Hello, and welcome to another episode of Mr. Boskin Does Some Math. Today we are doing illustrative math, grade 8, unit 8, lesson 7. Our first question here is a what do you notice, what do you wonder? A square and 4 triangles. So on the left we have a square and an outer square and 4 triangles around it. On the right, we have another square with 4 triangles around it that look to be isosceles triangles, maybe equilateral triangles. Would all these triangles be the same? Are all these angles the same? Are these 2 inner white squares the same? Well, especially this diagram with the blue looks very similar to what we've been doing so far, where we have been taking a outer square and enclosing a smaller angled inner square. So now let's look at our first problem today. Adding up areas. Both figures shown here use squares with a side length of A plus B. Notice that the first figure is divided into 2 squares and 2 rectangles. This has this square, and these 2 rectangles. Figure G has 1 inner square and 4 triangles around it. What is the total area of each figure? So how can we find the area? Well, for this one, this is the area model for multiplication. Some of you might remember from using before. However, here we don't have numbers that we're multiplying but variables. So let's see what we get when we use these. A times A is A squared. B times B is B squared. Those are both things we've done before. This is really similar to what we have been doing. Now these ones here are rectangles. How do we find the area of a rectangle? Length times width. Length times width for this one is AB. For this one, also AB. If you think of them as length and width, one of them might seem as a BA, but AB and BA are the same value. Oh, that was part 2. Part 1 is what is the area of the outer, the total area of the figure. So this side length, this is a square. The side lengths of this square are A plus B. What about on this one? Also A plus B, A plus B. So if we want to find the total area, we just have to multiply A plus B by itself or square it. So now what would we get if we perform this multiplication? A plus B squared is not just A squared plus B squared. What we have to do is distribute. A times A is equal to A squared. A times B is equal to AB. B times A is also equal to AB. and b times b is equal to b squared. Ooh, multiplying this one out, we got an a squared, an ab, another ab, and a b squared. So we multiplied out that total area, and that seems to match with that. Can we simplify any of this? Combine like terms? Yes, we can. A squared plus 2ab plus b squared. Because ab plus ab is 2ab. How about this one here? A plus b, b plus a, b plus a is equal to a plus b. So the total area of both of these squares needs to be the same. So this is our total area. Find the area for each of the 9 smaller regions. Well, we did that already for this one. How about this over here? Well, the way we've been finding the area of these inner squares is by subtracting the area of each of these 4 outer triangles from the area of this outer enclosing square. So this is right in line with what we have been doing. We now know the area of this outer enclosing square, so we just have to find out the area of each of these triangles. The area of a triangle is base times height over 2, a times b over 2. Now, there are 4 of those, so we could do a times b over 2 times 4. Keep them both as fractions. A times b times 4 is 4ab over 2 times 1 is 2. Let's simplify this. What's 4 divided by 2? Well, that's equal to 2ab. So now, if we want to find the area of this inner square right here, we have to do the area of the outer, a squared plus 2ab plus b squared. That's the area of our nice outer square. Subtract the area of these 4 triangles, which we found to be 2ab. Now let's simplify that. This works out pretty nicely here, subtracting 2ab, and this plus 2ab cancels right out. So a squared plus b squared. So the area of this inner square is a squared plus b squared. Okay, our next question here says add up the area of the 4 regions in figure F and set the expression equal to the sum of the areas of the 5 regions in figure G. So if we add up all of these and set it equal to all of these, we know that those have to be equal to each other. Now, let's try to modify what this looks like a little bit first. This inner square, as we talked about with our last lesson, the hypotenuse of a triangle, if we call it C, is always the longest side, which means the area of this inner square would be C squared. if we know that the area of these four triangles, as we already calculated, is 2AB. So now let's write the area of each of these full squares and see what we can simplify. I'll do it right here so we have some space instead of just underneath here, because it'll be nice to be able to see these figures. So the area of this one is equal to a squared, which is this square, plus b squared, which is this square, plus 2ab, which is this ab plus this ab is 2ab's. That has to be equivalent to our other square right here. And that square, we know this inner space here is c squared plus the area we calculated for these four outer triangles together was 2ab. So now, is there anything in here we can simplify? Well, each side of this equation has a 2ab. So let's subtract 2ab from each side. Those cancel out and those cancel out, and we are left with a squared plus b squared equals c squared. This is what we talked about in our last lesson, is the Pythagorean theorem. So the little bit of math we did up here proves that the length of a squared plus the length of b squared has to equal c squared. So the sum of the square of our two legs, our two shorter sides of this right triangle, have to equal c squared, the square of the hypotenuse. Today's Are You Ready for More problem is a little bit of a challenge. Take a 3, 4, 5 right triangle, add on the squares of the side lengths, and form a hexagon. What is the area of this hexagon? 1, 2, 3, 4, 5, 6. That's a six-sided figure. What's the area of it? Well, first, what else do we know here? We know if these are squares, this length also has to be 3, which means this length also has to be 3, which means this length also has to be 4, this has to be 4, that has to be 3, that has to be 4. So that let us... that should have been a 4. Because those are both 4. Well, what else do we know? We can enclose this 5-unit square like we've done. And then this has 4 congruent triangles around it, which means if this distance is 4, this distance here also has to be 4, which means that also has to be 4. If this side has a length of 3, that means this side also has to have a length of 3. If this is 4, then this is 3, so that is 3. Which means that's 3, so this side is 4. That distance is 3, that distance is 4. This distance we already knew was 4. That distance is 3, which means that distance is 3. And now we can find the area of this whole outer rectangle. This is 4, and 4 is 8, 9, 10, 11. That's 11 units. Let's double check the other side is the same. 4 and 4 is 8, 9, 10, 11. That's also 11 units. That checks out. Now let's check top and bottom. 3 plus 3 is 6, plus 4 is 10. The length of the top is 10 units. The length of the bottom, 3 and 3 is 6, and 4 is 10. So this total white area, including our hexagon, is 10 times 11, which is 121 units. Now we just need to subtract the area of each of these triangles. Well, this one here is 3 times 4 is 12, over 2 is 6. This triangle right here is also 3 times 4, which is 12, over 2 is 6. So that's an area, that's an area. Now we have these triangles on this side. This one here is 3 units by, that's 4 and that's 4, so this is 8 units. 3 times 8 is 24, over 2 is 12. This one here, 4 times 3 plus 3 is 6. 4 times 6 is 24, over 2 is 12. So the total area is 121 units. And then we have to subtract 12 and 12, which is 24. And then 6 and 6, which is another 12. So 36. So we have to do 121 subtract 36, which is 85 units. So the area of this colored hexagon is 85 units. Now our next part here is, let's take this for a spin. Using our big idea of a squared plus b squared equals c squared. Move that down so we've got a little bit more room. A and B, we remember, are always our two legs. And C is always our hypotenuse. So let's substitute those values into our equation. If A is 5, A squared is 5 squared, B is 2, equals C we don't know. Actually, they labeled it as X, so let's keep it as X. Now we just need to solve this equation. 5 squared is 25, 2 squared is 4, equals x squared. 25 plus 4 is 29, equals x squared. Well, if x squared equals 29, what is x equal to? Well, we need to get the x by itself, so we have to undo squaring. The inverse of squaring is a square root. Squaring and square root here will cancel out. This is an irrational number. Which means we get to be lazy and leave that as the square root of 29. Okay. On this one, let's label them. Opposite the right angle is the hypotenuse, which is always C. Let's call these A and B. Substitute those into the Pythagorean theorem. Square root of 8 is A squared plus B squared equals C squared, which is 4 squared. Okay, now let's solve this equation for B. Square root of 8 squared is 8 plus b squared equals 4 squared is 16. 4 times 4 is 16. Now what do we have to do to get this b isolated? Subtract 8 from each side. B squared equals 16 subtract 8 is 8. To isolate the b, we have to get rid of the squared, which means we take the square root of that, do it to one side, do it to the other. Squaring and square root will cancel each other out. B is equal to the square root of 8. Which means y is equal to the square root of 8. Which makes this an isosceles right triangle. Quick summary of this lesson. The figures shown here can be used to see why the Pythagorean theorem is true. Both large squares have the same area, but they are broken up in different ways. This is what we did before. This is true for any right triangle. If the legs are a and b and the hypotenuse is c, then a squared plus b squared equals c squared. This property can be used any time we can make a right triangle, for example, to find the length of a line segment. Here's a line segment on a grid. The grid can be used to create a right triangle, where the legs of this right triangle are 7 and 24 units. Since this is a right triangle, 24 squared plus 7 squared has to equal c squared, which makes it so that c is equal to exactly 25. So a squared plus b squared equals c squared. That's our lesson for today. This has been another Mr. Boskin Does Some Math. Thank you for tuning in. See you next time.